Donor work with Lin Xiaohuang from Tsinghua University and Piano from Shanghai University of Finance and Economics.
I'm sorry, we still can't hear.
Oh, okay, then keep louder. Okay. So I will start with the problem of counting matchings, and this is of fundamental importance to this work. So it's a well-known problem, and it is sharply hard, and we know there is a FP rust to approximately count the number of matchings. And so I think for this audience, I don't need to explain what is FP rust, and so a very general method to design FP rust is to first decide a sampler that can uniformly sample from the set of matchings in the graph, and then there's a general procedure to transform the sampler to FP rust. So in light of this, JERRUM-SINCLAIR defined a Markov chain to uniformly sample from the set of all matchings. So I'm going to describe this Markov chain first, because the main purpose of this work is to generalize this Markov chain to other counting problems. So suppose now we are at some matching M, and we are going to decide what is the matching M prime in the next step. So the Markov chain works as follows. So first, it is a lazy Markov chain. So with probability 1/2, we will have M prime equal to M, and otherwise we can randomly choose an edge E equal to UV, and there are 4 cases. So suppose this is the current matching we are at. So if E is just edge in the matchings, then we can remove this match from M and obtain our new matching M prime. So this operation is called remove, and similarly we will have 2 other operations: add a new edge and replace the edge by a new edge. So this is the Markov chain, and we are interested in the mixing time of this Markov chain. So we have to fix some notations. So in the following, we are working on a graph with n vertices, and we use omega to denote the family of all matchings in this graph, and we use pi to denote the uniform distribution. And we also use this P to denote the transition matrix of the chain, and we can define what is called rapid mixing. So I think most of us are quite familiar with these definitions. And in order to prove a Markov chain is rapid mixing, a very useful technique is to define a so-called the canonical passes. So we can look at the configuration graph of this matching. So in the configuration graph, each vertex is a matching. So suppose we are working on a graph with 4 vertices. So this is the configuration graph, and we have an edge between a pair of matchings if we can move from this matching to the other in one step in our Markov chain. And with a canonical path is, so for each pair of matchings, we want to define a set of passes from X to Y, and we want to assign a weight to each of these paths. And this weight are required to satisfy this equation. That is, for every pair of matchings X and Y, the summation of weight of paths connecting X, Y must be the same as the pi of X times pi of Y. So if we have a set of passes satisfy this requirement, then we say the family of this path, the canonical path for this Markov chain. Okay, so what do we mean by a good canonical path? Intuitively, it means that we want to design this path distributed averagely over all the configurations. So we can consider the notion of congestion of an edge. So we can consider edge in the configuration graph. So each edge is a pair of matchings, and we can consider the summation of all the passes crossing this edge. Then the summation of all the weight of passes crossing the edge over the capacity of E is defined as the congestion of this edge, and the congestion of a canonical path is the maximal congestion over all the edges. So, and we know that if we can somehow define a canonical path which whose congestion is bounded by some polynomial, then we can show this Markov chain is rapidly mixing. So this is what we know, and in the next I will describe the canonical path for the JERRUM and Sinclair's chain for sampling matchings. Okay, so and then I will talk about how to generalize these two other problems. So consider now we have a pair of matchings in the configuration graph. So this is M and M prime. So the first thing we do is to take the symmetric difference of these two matchings. So since the M and M prime are all matching, so we will obtain a graph which consists of disjoint cycles and passes. Then we can define some canonical order of this component. So say we can first choose this component to the cycle and then choose the path. Then we have an operation of unwinding, which means we can first choose this edge. So remember, we want to move from the red matching to the green matching, and we can start from this cycle and start from these red matchings, and then we can remove this edge, and then replace this green edge by the red edge, and replace this green edge by this red edge, and so on. So after we finish this cycle, we can do the similar things for this path. So in this way, in this canonical way, we can change from the M to M prime. And in fact, in this way, we can define a canonical path connecting every two pairs of matchings. And in fact, this canonical path has a very low congestion. So I'm not going to give a detailed analysis of this congestion, but the fact is this is a very good canonical path. So we just want to generalize this to some other problems. So the framework we are going to work on is the HOLANT problem. I think in previous talk we know what is a HOLANT problem. So here we consider a HOLANT problem is specified by a family of functions. So we have an instance is a graph G, and each vertex is associated with a function which is in this family. So in this case, we only work on the Boolean functions, just like the case of matching. So each edge is either 0 or 1. And so for each configuration, we can define its weight, which is the product of values evaluated on each vertex. And then the problem is to compute the partition function, which is the summation over all the weight of configurations. And we are also focused on the symmetric functions, which means these functions, the value of a function f only depends on the Hamming weight of the input. Okay, so for symmetric functions of array m, we can write it in this compact form. So where fi is the value of f on input with Hamming weight I. And so, for example, the problem of counting matchings can be understood as the HOLANT problem with every f width of this form. So we only allow at most one of its incident edges are chosen by the configurations. So I'm going to introduce the notion of WINDABLE functions. So this is defined by McQueenan and aimed at generalizing the sampling algorithm for counting matchings. And so his definition is quite technical. So before introducing the definition, I have to introduce some additional notations. So here is the notation we call the partition. So suppose J is a set, and we have a 0, 1 vector x defined on the set J. Then we use script m sub x to denote the set of partitions on the support of x. So the definition would be clear if you look at this example. So say in this case J is 1, 2, 3, 4, 5, and we have a vector x which is have value 1 on position 1, 3, 4, 5, 6. Then mx is the following set. So each element of mx is a partition of the support of x into pairs. And in case that the Hamming weight of m is odd, we can have at most one singleton. So this is definition of mx. And now we can introduce the definition of windable functions. So the windable functions. So here's so this definition seems to be quite technical if it's your first time to look at it, but it's quite natural if you understand what the Markov chain on windable function is going to be. So let's look at the definitions. So we say a function f is windable if there exists some value b. So the value b are indexed by three parts. So the first part is a input x and another input y and a matching m. So what is m? M is a matching in the support of x or y. So remember the notion we defined before. And those value b are required to satisfy these two conditions. So what does these two conditions mean? So essentially this definitely captures the way one wrote flows in the canonical path argument. So remember in the case of matching, we have a matching m and a matching m prime, and we want to construct a canonical path from m to m prime. The first thing to do is to consider the symmetric difference of m and m prime. So here, for input x and xy, we consider the symmetric difference of x and y. And I claim that for each m in this set, it corresponds to a canonical path from x to y. And the weight of this canonical path is proportional to the value b, x, y, m. And so then you look at the first condition of the windable. So it is almost identical the requirement for a canonical path. So this is the intuition behind these definitions. And the condition 2 is just allows us to apply a flow encoding argument to show the low congestion of this canonical path. So in this talk, I'm not going to talk about the detail of the second part, but we are mainly focused on why we have a natural condition 1 here. So this is what we are going to do. And so now, given these conditions, we can have a class of functions which we call windable, and then we start to design Markov chain to sample from those windable functions. In order to work on this, our configurations are on the so-called half edges. So consider a graph. We break each edge of the graph into two half edges. So just like this. And we have many class of configurations. We use omega k to denote the set of configurations with k inconsistent edges. So in the following, we will use red edge to indicate this edge has been assigned value 1, and the black edge as to indicate this edge has been assigned value 0. So this is alignment in the configuration omega 1, since we only have this edge, which have inconsistent color. Yes. And this is the configuration in omega 3, since we have three four edges which has inconsistent color. So is this clear? Okay, and so our Markov chain just run on the space of omega 0 and omega 2. So our Markov chain is by a simple Metropolis rule to move between these between configurations, and we only move between configurations whose Hamming distance is exactly 2. So this rule is simply the Metropolis rule, and so it is reversible and converges to the desired distribution. And we have an additional step to make this Markov chain lazy. So we add some probability to state at sigma. So with this Markov chain, McQuillan shows that with this Markov chain, if every function f is windable, then this Markov chain is rapidly mixing. Okay. And as a corollary, since our sampling space is omega 0 union omega 2, so if this Markov chain is rapidly mixing and we have this additional condition, that is the weight, the ratio between the weight of omega 2 and the weight of omega 0 is bounded by some polynomial, then we can efficiently sample from the omega 0. Since remember the definition of the omega k, the set of omega 0 is what we would like to sample from. So if we have this additional condition, then we have a FP-RAS to compute the partition function of this HOLANT problem. So in order to analyze this Markov chain, we have to look at the canonical paths defined for this chain and these windable functions. So suppose we now have two configurations. The first is from omega 0 and the second is from omega 2. And then we want to define the canonical paths from x to y. So the first step is to take the symmetric difference of these two configurations. Okay, so for this simple example, so their symmetric difference is just the same as y. Okay. So then our configuration is just an alignment on the half edge. And then remember that we claim that for every matching on a vertex corresponds to a canonical path. So, but these matchings are defined on each vertex. So suppose now we can fix a matching on MV for each vertex V in this graph. So in this figure, I think I try to show these matchings. So consider this vertex, then so we have three edges. So we don't have a full matching. We have two edges matched and with a singleton edge, right? So we use this blue dotted edge to indicate the matched edge, right? And for this degree 4 vertices, we have two pairs of matched vertices. So now we fix such a matching for each vertex. Then we can construct a new graph. So this new graph, the vertices of this new graph is a set of half edges. So the red edge in this graph is the vertices of our new graph. And the edge of the new graph consists of two parts. The first part is the blue dotted edge. It's the edge in our fixed matchings. And the second part of edge is those edges connecting half edges. That is this black dotted edge. So then in this way we can construct a new graph. And it is easy to see this new graph also consists of disjoint passes and cycles. For example, in this graph, we have two passes. So first this edge, then this edge, and then this edge, and then this edge. So this is a path, and we have another path is this edge with this edge, and we have one cycle. So it's this edge, this edge, this edge, this edge. So in this example, we have two disjoint passes and one disjoint cycles. And we can also fix some canonical order to unwinding these configurations. So for example, we can first choose this path and change these two configurations, and then change these two configurations. And after finishing this path, we can start with this cycle. First, change this pair of edges, and this pair and this pair, and finally we change this path. So in this way, for each fixed M matchings on each vertex, we can define a way of routing from X to Y. And the weight of this canonical path is just the product of B value. Remember, these B values are values witnessing each vertex V is windable. Okay. So this is our definition of the canonical path for windable functions. So in this way, if we apply the second condition in the definition of the windable functions, we can prove this condition. We can prove this canonical path has no congestions. But if you look at this proof, you can see, well, the definition of windable functions just pose some conditions saying that some kind of canonical path argument applies, but it doesn't tell you how to decide whether a function is decidable, right? So if you want to apply directly apply this definition of windable, but to decide whether a function is windable, it's not very easy. And in the work of McQueen, he gives a few examples of windable functions. But even for some very simple functions, he needs to have a very complicated construction of this value b. So we study a special class of functions, the set of symmetric functions, and we can show that at least for these symmetric functions, the windability has a very simple characterization. So first, consider a symmetric function fx written in this compact form, and we say a pinning of this function is just a subsequence of this truth table of these functions, and we say. And we have a following characterization theorem for the symmetric functions. So we say a symmetric function f is windable if and only if we consider every pinning g of f, and for each pinning g we can define a function h, where h of x is g of x times g of x bar, where x bar is obtained from x by flipping every position. So in the case that g is a symmetric function, so if x, the Hamming-weight of x is I, then the Hamming-weight of g bar is m minus I. So for each pinning of g, we can have a function h, and we require that for each h, this linear equation has a non-negative solution. So this is a characterization of the windability. And so the matrix A is defined as follows. So in fact, what does this mean? So consider the entry of Aij entry of the matrix AM. So it has the following combinatorial interpretation. So consider we have a m labeled balls, which means each ball are different. And I of these m balls are red, and m minus I of these balls are blue. And then aij is just a number of ways to partition these m balls into pairs. So in case that m is odd, we can have at most one singleton. So aij is a number of ways to partition m into pairs such that the number of pairs with different colors is j. So this is a number given, and it can be computed in this way. So this is our definition of the matrix A. So with this characterization theorem, given a function f, in order to decide whether it is windable, we only need to check every pinning of G, and the H obtained from G. We need to check whether this equation has a non-negative solutions. So I will sketch the proof of this characterization theorem. Since we are only this theorem only applies to symmetric functions, and so we can in fact, the crucial observation is that for each x and y, we don't need to consider too many values of b, x, y, m. So we can classify matchings in the partitions of x or y into some equivalent classes. And suppose the Hamming weight of x or y is m, then each equivalent classes can be indexed by some I and j. And we show that if a function f is windable, then there exists a family of these b values such that for m and m prime in the same equivalent class, these two values are the same. Then the value aij in the definition of matrix A is just the number of elements in the equivalent class indexed by I and j. So in this way, we can reduce the task of finding the value bxym into the task of solving a system of linear equations, and we just take the solution x as our value for this b. So the requirement for this x is that they are all non-negative. So with this tool, we can have some examples. So first is the matching functions. The matching is a function of this form, and if we want to apply our characterization theorem, we only look at the pinning of G and the H obtained from G. So for functions of this form, the probability of H are only 3. So we only look at these 3 simple functions, and to check the a1 times x equal to 1 and a2 times x equal to 0, 1 have non-negative solutions, and this can be easily done. And for the second condition, so remember in the corollary of Macqueen's theorem, we need another condition, that is the ratio between the weight of omega 2 and the omega 0 is bounded by the polynomial, and this is also very simple for the example of matchings. So given these two equations, the solution of these two equations, we can conclude that there is the FP-RAS for counting matchings. And the second example is the so-called subgraphs word. So the subgraph word was introduced by JERRUM and Sinclair to approximate the partition function of EC model. And it is, in fact, a HOLANT problem with parity constraint. So in each vertex, the constraint is of the form 1 mu for some non-negative mu. So if we look at this kind of function f, and the pinning of f and h obtained from G, there are 2 probabilities. Depends on the parity of the parity of G. the first one is the O1 function. The second one is also a parity functions, and it is also very easy to check. We can for function of this form, we can solve our equations, and we can check this f is windable. So at least with this with this characterization, we can say that at least for the case that mu is positive, we have FP-ROS for the subgraph word.
Question. So for subgraph words, you would also have edge weight.
Yes, I will explain edge weight later. Yeah. And so we have known these two FP-ROS before, and now I'm going to talk about some new examples, new algorithms. So the first is the problem of B matching. So given the graph G, and the problem of B matchings is, we say a configuration, the B matchings, if for every V at most B of its incident edges are chosen. Okay, so the matching problem is the one matching, right? So if we write it as a HOLANT problem, then the constraints are of this form. So we can apply our theorem to check for what B this problem is windable. And for every constant B, the opinion of this function only have constant number of probabilities. So you only need to check a constant number of linear equations to see whether the function is windable. And we can show that B matching is windable if and only if B is at most 7. And similar, we have the ratio bound, and so we have for B at most 7, the problem of counting B matchings have a FP-ROS. And the second example is the so-called B edge covers. So edge covers, which is, so for every vertex V, we have at least B of its incident edge that chosen by sigma. So in the case of matchings, we have at most B, and in the case of edge cover, we have at least B. So in this way, we can also have we can also apply our characterization theorem, and we can obtain the following result. So the B problem of B edge cover is windable if and only if B is at most 2. So we have that the B matching for B equal to 1 or 2, let's say FP-ROS. And we have, and so for all the FP-ROS we mentioned, we have the following. We can extend them to the edge-weighted version. Since we can just subdivide each edge, and we add a constraint 1, 0, and the weight of E to these vertices. And since this function is also windable, so we can arbitrarily add the edge weight to each edge. So all previous FP-ROS can be extended to the edge-weighted versions, as long as the ratio between the two class of configuration is bounded. So this is the FP-ROS we obtained from this method. And now I'm going to talk about some future work in this line. The first is, can we decide the windability for some other HOLANT problems? So we are focusing on the HOLANT problem with the Boolean domain. So a class of problem we have considered is the Fibonacci gate. That is the functions satisfying this recurrence. And remember that the parity function is a special case when C is equal to 0. And we can show, in fact, this class of function is windable for a sufficiently small C. And so this is the I think the interesting question is can we identify some other class of Boolean HOLANT problem which is windable and can design FPRs for this using this tool. And the second point is that the windability and the match gate. So McQueen proved the following theorem about the windability and the match gate. He shows that we consider all the functions realizable by a match gate. Here, a match gate is not necessarily planar, and it can use the constraint of the matching and the perfect matching. He showed that every function realizable by this match gate are windable. And he also showed the converse direction of this theorem for functions with arity at most 3. So, which means for all the functions with arity at most 3, it is windable if and only if it can be realizable by this kind of match gate. So the question is whether for the functions with higher arity, can we still have these directions? So in fact, this theorem gives a way to check whether a given function can be realized by a match gate of this form. So for example, we have shown that the 8 matching is not windable. So using this theorem, we can say that the 8 matching function cannot be realized by a match gate of this form. So I think it is very interesting to investigate the converse direction of this theorem, and we are even not able to prove except using the definition of windability, we are not able to show some function is not realizable. Cannot be realized by some match gate. We don't have any tool to achieve this. So I think in order to prove or disprove this, we maybe need some new technique to understand these functions. And that's it.
So I kind of wonder, is this windability preserved by, like, say, holographic transformations? Because if I remember correctly, Fibonacci gates are equivalent up to orthogonal transformations for different C. But here you're saying, like, only for small C is windable, for large C it's like not, right?
Yeah, I think
equivalent under some transformations. So.
Yes. So I think there's no reason for windability to be preserved under this reduction.
So it's not necessarily invariant under these transformations.
So do you believe that they're equivalent, windability and realizable match gates, or is, like, which direction do you move this?
I don't know. So in fact, we have tried some windable function and we try to realize them by using some match gate. But for some function, we can't construct such a match gate. So
you're not allowing edge weights in these match gates, right?
we allow the positive edge weight.
Because if you allow
Yeah. So in fact, we know that some function like equality it is not windable, and it cannot be realized by match gate with only positive weight.
So what about B matching with 1,000? B equals 1,000. Is there any evidence for intractability or?
We believe that the B matching is always approximable, but not using this method. Yeah.
So let's thank the speaker again.